Hi folks, this is CEO speaking again. Nice to see you back. Infrared remote controls. What do you have in your home? You have TV sets, thermopumps, air conditioning systems, kitchen hood, ceiling fans, portable ones, portable heaters, air purifiers, dehumidifiers, and so on. The most of them are provided with a remote control. Something like this, or something like that. And inside, all the objects the remotes are controlling, like TV sets, you're going to find such a thing, which is an infrared receiver, okay? And all of them, they have 3 terminals like this, okay? I put it here in a socket. And the purpose is not to check the TV set or the kitchen hood and so on. The purpose is to check the remote because, unfortunately, they are physically abused the most of the time. You drop them, you kick them, some of them, they drink part of your coffee and so on. So sometimes, if it's not the battery which is the problem, and there are certain keys you are not sure about, you might want to make sure they're working fine. So I built here a little project. So let's find out how do we check it. We connect the power supply. Any standard 5-volt power supply will do. And if you put it on, then by pressing any button of your remote control, you're going to see the light going on anytime you press a key, any key. And also there is a little piezo electric beeper somewhere here. I have a whole bunch of them in a box, different kinds, okay? And this one is gonna make a noise, telling that the control is working fine. This one is from a portable fan. You see here is showing the fan blades, okay? If this discrete sound I like is not enough, no big deal. We can do something about that. We have a jumper here, and if we change the position, we can make it very annoying. Or this one here, very annoying. Hey, some of you may not be even happy with this one, okay? Not with the discrete one. Don't worry about it. We can make it much more interesting. Here is a standard 3.5 millimeter jack for the earphones. We connect it over the audio system and take a look now. In the moment you put the power on, you make sure that the remote is working fine. Okay, so obviously you won't need to go that far, okay? So let's make it quiet. And we're going to replicate the discrete one. Now, how do we make such a thing for checking? It's very easy. Actually, there are gonna be 3 stages related to that. One stage is regarding the sensor itself. Another one is controlling the light, and the other one is controlling the sound. And in order to build such a thing, we're going to use one package, only one integrated circuit. I chose for this project the 74HC132. It's made of 4 NAND gates, like this. The little symbol inside is a Schmidt trigger. And you can also use another kind of package similar to that, which is a classical 4th generation CMOS 4093. But be careful because there are at least 2 major differences between them, even if both of them are CMOS, is that the 1st generation CMOS can be energized between 3 to 15 volts. And this one, the HC series, can be energized between 2 to 6 volts. Now we are going to relate to what the sensor is asking. The sensor is energized at 5 volts. So both of them are going to be able to receive 5 volt. but obviously they are not in the same range of voltage as done by the manufacturer. And the second major difference between them, as you can see, the way the NAND gates are aligned inside the package, these two ones here are aligned the same way, these two, but not the other two. So please be very careful, because I chose this one here. If you choose the other one, you have to change the wiring on the breadboard. So far, so good. We're going to use this one. So let's start. We're going to start with the sound. And in order to make your life a bit easier, we're gonna build one stage at a time, because if you do that, you do the troubleshooting at the same time as you build the stage, instead of wiring the whole thing in one shot and then asking yourself why it is not working. So let's see. Here we're going to use a toggle switch. With the toggle switch here, we're going to simulate the source of signal, which is the sensor. So by doing this, take a look what we are going to do with that. Here I'm going to draw just one of the 4 NAND gates. I'm gonna signal here, it's a Schmitt trigger. And we're going to build a little oscillator, because we need to generate some sound, okay? And this is going to be made an extremely simple one. It's difficult to imagine a simpler sound generator oscillator, simpler than this one. It contains 1 resistor and 1 capacitor. The resistor is connected in a feedback loop across the gate. However, in series with that resistor, we put here a trim pot, because we want to adjust the frequency. I'm going to tell you about that soon. So this is 4.7 kilo ohms. The trim pot is 10 kilo ohms. The capacitor is 22 nanofarads. We just want an audible frequency we're going to be able to adjust. Okay? And then we're simply having a transistor. When the resistor in the base of the transistor is below 20 kilo ohm, you know for a fact that the transistor is working like a switch, so it's going to go in saturation. Let's find out. Here is going to be the positive line. We said the positive line is 5 volt. And here we're going to have 2 things. We're going to have a DC load, which is a resistor. And in parallel with it, we're going to have our piezoelectric transducer, the beeper. So piezo transducer, okay? Any PNP transistor you have at hand can be used. North American versions to N2905, 2906, 2907, just to pick up examples. European versions BC448 or 557, okay, just to have examples. So this is the transistor, this is the gate. So we're gonna put here pin numbers, and just to make sure, pin number 7 goes to the ground, pin number 14 goes to the power supply for the package. Package name again 74HC132, okay? So that's the circuit. And again, with the toggle switch, we're going to simulate the source of signal. I wired this one already for you. We're gonna put it here. And what do we have? We have 2 external things. We have a switch and we have a trim pot. Instead of trim pot, I'm gonna use a potentiometer. So I hope you remember the previous video where by using an external arrangement, I'm going to use this potentiometer here in the middle because it's 10 kilo ohm, and that switch here. So what I'm going to do, I'm going to connect them over here, like that. And we're going to also connect the power supply, the ground, and the positive. Here is the package, the integrated circuit. The capacitor and the resistor are right here, the ones making the oscillator. And here, through the cable, I'm reaching the potentiometer connected in series with that resistor and the switch. So when I energize it, you hear the sound, okay? So what do we do with the sound? We can adjust by using the potentiometer just to catch the resonant frequency of this beeper until we can hear the sound louder, just a bit. You see, we can modify the frequency. We're going to keep it like that, okay? So again, the switch is simulating the source of the signal. So now, because the switch is off, there is no signal, so the transducer is quiet. So this is how we work with the piezo beeper. Of course, again, in case you want it a bit louder, I can use a module recovered from an old computer, this one here. And this one, obviously, is going to make a bit more noise. Okay? And how the circuit is going to look like if you use such a thing, because this one basically are having 3 pins. You take a look, one of them is a red wire, another one is a black one. So these are the power supply, 5 volt and the ground. And the green one here, I connected a pin to it, is going to be the input for the amplifier. Okay? In case you use such a thing instead of the transistor in our diagram, let me find out how is this on a diagram. It's gonna be something like that. We have here the toggle switch. This one won't change. Okay. It's going to be the same kind of gate, the NAND gate, with the capacitor, which is 22 nanofarad, the 2 resistors here, the 4.7 kilo ohms, and the trim pot 10 kilo ohm. The same gate, the same NAND gate okay, and then we're going to just have, I'm going to draw it like a box. So I'm going to call this a sound module. Here at the end of it is the speaker. So it has a ground. It has a positive. The positive comes together with the top of the toggle switch, a plus 5 volt. The other end of the toggle switch goes to the ground. So then, this is the sound module. Let's call it sound amplifier, as well as this one here, sound amplifier. Okay, good. So the circuit is absolutely similar to the previous one, but instead of having the transistor amplifying the sound, we have that external module you can use from an old computer if you dismantle it. Good. So once we have this one, we clarified the thing about the sound. Now we can have the module to control the light. So the module to control the light, similar way, we are going to have the toggle switch, and this time we're going to have another NAND gate. Here is the plus 5-volt line. Please notice that anytime on a NAND gate, one of the inputs being related to the plus 5-volt, then the NAND behaves like an inverter. Okay, so this is an inverting buffer, actually, this one. Okay, so we're going to have this one right now. Let's say 6, 5, 4, and 6, the output, the same kind of package, okay? And then we're going to have the resistor about, I forgot to put here the unit, sorry, kiloohms, 10 kiloohms, and then the transistor, the same kind of PNP transistor, but this time the PNP transistor is going to control an LED. That's an LED, and the resistor here is 1 kilo. And that's it. Take a look how simple it is, you know. So if I want to make sure, I'm going to circle all that, and this is the light control. Okay. So here I prepped this one also for you. So this one right here, this time I only need the 3 wires for the switch. The 3 wires for the switch, I have no need for a trim pot. Take a look how simple it is. And then we're going to connect our external switch right here. We're going to connect the power supply. The negative and the positive. We put it on. And then having the switch. You see this? Anytime I move the switch, I control the light. Remember, the switch is just simulating what? The sensor stage, okay? Good. So once you just build that very little diagram here, you notice now that we don't even need to use all the 4 NAND gates of the original package. We only need to use 3 out of 4, okay? So now, how do we put all these things together to build our project? Take a look how. We disconnect the external components, the ones we did in the last video, okay? We disconnect the power supply from here, and we have it already assembled in one shot right here. So here is a sensor. The infrared sensor is working at 38 kilohertz, this one, exactly like the other one. Take a look, they are identical, okay? And I'm gonna replace this one in the socket. And then this one is the whole diagram. We're going to just need to connect the power. And I'm gonna show you the diagram in 1 second. I put it here already because I want you actually just to know how the stages are connected together. You take a look. The stage about the light is this one here, and is this one in the top. Same, okay? Now, this is the stage about the sound, this one in the bottom. But on the pins which are not connected nowhere right now, this one and that one, we were having what? We were having before the switch controlling either the light module or the sound module. But right now, what's going to happen is Here is the sensor. The sensor model is TSOP 1738. The last two digits 38, they refer really to the frequency 38 kilohertz. Okay? And the way the sensor is connected, I'm going to talk a bit later about the sensor specifically. It has three terminals. One of them goes to the ground. The other one goes to the power supply. Be careful, because in some diagrams you are going to find here an additional resistor about 47 ohms, not kilo ohms, 47 ohms. This is just put there sometimes to reduce the disturbances coming on the power line. And the output of the sensor is the pin number 3. So remember about the gates. Anytime the gates, like this one or that one, they have a pin connected or tied to plus 5 volt to the power supply, they behave like inverters, controlled inverters. Okay? So they are inverter buffers right now. So here, through that little inverter right here, the signal goes in two directions, is actually distributed in two directions. One goes here, because you need the light to show you if the signal is okay. And the other one goes right here in order to augment with signal the stage for the sound. And that's how the two of them are related together and to the sensor. So this is what you need to do. There's a diagram actually. It's a very easy one to do. Okay? So let's find out. If this one is connected properly and the power is here, we put it on and now we check it. You can easily hear the sound and you can see the light exactly like on the project already wired. Okay, so it doesn't take much room. One transistor here, okay, another one right here. This is for the light, this is for the sound, okay, and it can also serve as a checker if you want for different or variety of piezo beepers. So you can check all of them by just connecting them instead of this one here. Okay, and the job is done. Now, the last thing I want to talk about is a bit about the sensor. Okay, let's put this aside. Let's say you don't want to build all that, even if it's a very simple circuit, only one integrated circuit and two transistors. You want to refer to what the manufacturer says, okay? I'm gonna make it here a bigger diagram. Let's say this is the sensor itself, TSOP 1738. It has one terminal here, one here, and spaced out is this one. Terminals are numbered 1, 2, and 3. The one is for the ground, the second is for the 5 volt, and the third is for the output signal. Okay? So, in that situation, if you just connect here a resistor and then you connect an LED, so you have here a resistor and an LED. The resistor can be 1 kilo ohm. You have to keep in mind that the output of this receiver can sustain a couple of milliamps, so not much. For that reason, you put here a 1 kilo ohm resistor, because if you power it at 5 volts, the voltage across the resistor is 5 volt minus the forward voltage of the LED, because if you put a standard LED, we discussed some time ago, is about 2 volt. So this is approximately 3 volt. So if you can take a look, 3 volts here and 1 kilo ohm the resistor, the current into the resistor and into the LED is going to be 3 volt over 1 kilo ohm, so it's 3 milliamps, okay? So you have to keep it very low. If you want a bigger light, like this one here, 15 milliamps or 20, then you need to build our project. But if you want to do only this, it's gonna be something like that, okay? the ground here, and here is going to be the plus 5 volt. And then chances are this is an LED, standard color, green, red, amber, okay, or yellow. So these are the standard colors. If you do this, it's supposed to work, okay? So let's do this very quickly. I'm gonna pick up this one here, and we're going to build it right here in a corner, okay? I'm gonna pick up a sensor, okay? So I'm gonna plug it anywhere here, and I'm going to pick up a resistor, and then the LED, and then 2 wires, one for the positive, the other one for the negative. Okay, and that's it. So now if I energize my circuit, remember this sensor is made for 5 volts, not 9 volts, not 12 volts, 5 volt, okay? Otherwise you can damage it. So I put it on, forget about this green light, and now if I press, you're going to see it very tiny. Take a look. Anytime you press a key, it's going to work, okay? However, because this is a very tiny light and there is no sound indication, this is why we prefer to wire our project, okay? And especially for beginners, that circuit here may be very tricky. If you don't energize it exactly with 5 volts, so you need a source of energy exactly 5 volts, because if you don't, 2 things may happen. Either you can reverse accidentally the power supply terminals. So in some diagrams, you're going to find here a diode, a rectifier, connected like that. And here is the power supply. It should be 5 volts. So this is a rectifier, it's not an LED. So if you accidentally reverse the 2 leads of the power supply, if the negative comes here, nothing is gonna work, so you can protect your circuit. But instead of having a rectifier, which is usually in the series of the 4000, 1N, 4001 up to 4007, I would recommend you to put a Schottky diode, like 1N 5819, just to take an example. Schottky diode. What is the advantage? Is that anytime you have a diode connecting to a circuit, it takes some voltage. So the forward voltage for a standard silicon diode is around 0.7 volts. So you lose 0.7 volt from the 5. While the Schottky diode, the forward voltage is around 0.1 to 0.15 volts. So it's just a very low drop for the diode, okay? So this is what you should do if you want to use this diagram, which is even simpler than our project, okay? I'm gonna put this one, even if you have access to the manufacturer specs, I'm gonna put this one in a folder and I'm gonna give you the link, okay? So let's see it one more time before we leave. Okay. So we check it out. Any cue press. This was the checker for the infrared sensors. Thank you very much for watching. See you next time. Bye-bye.